and giving this presentation. So I'm just going to kind of lay it off to the side. It should still be working.
Yeah, thanks for inviting me.
Yeah, no.
Okay. You're always welcome. Certified member and everything.
Yeah, I got a badge.
Yeah,
Yes,
you're
I'm
official.
here. It's awesome. Okay, so yeah, I'm Lani. I went to the University of North Georgia for my bachelor's and got my physics degree, and now I'm at UTC with the graduate school, and I'm in the quantum center. So we're doing a lot of research in quantum mechanics and quantum physics, and a lot of quantum stuff is in the news right now. People talking about the quantum internet and networking. We do a lot of collaborative work with EPB and Oak Ridge, the national lab. But my interest is in astronomy. So my advisor and I came up with a PhD project that I could do that has this quantum physics and applications in astronomy. So I'm going to talk a little bit about that and sort of what some people have already done so far. Okay, so first I want to ask, has anyone seen this before?
Yes, image said.
Yeah, it may be 7. It's the supermassive black hole that was imaged by the Event Horizon Telescope in 2019. And the reason I wanted to point this out is because they used a really specific method to get this image. It wasn't in the optical wavelength. It was a radio telescope that they used, and they used a technique called interferometry. So sorry, this should be kind of moving. Well, interferometry, we use light waves and how light will interfere with itself and make measurements off of that. So this is a typical basic setup of an interferometer. We have a laser, and the light gets split by a beam splitter, and it hits 2 different mirrors, comes back and recombines to create what we call an interference pattern, and we can see it here. And because we can model light as a wave, if there's 2 light waves that are stacked on top of each other, they will interfere constructively and create a bigger wave. But if they are out of phase, they will destructively interfere and create no wave. So that's what we see here with the light rings. That's where the light is overlapping and creating a bigger wave, or a wave that we can see. And then the dark ones are where the light is canceling out when it recombines here. And we use interferometry in astronomy and in a lot of other fields, but this is a good kind of visualization of what's really happening. So you see the laser comes in, and this is actually how LIGO works. If you know the observatory that detects gravitational waves. So we see the light gets split up by the beam splitter, reflects off of the mirror, and when it recombines, now it's out of phase here. And depending on how much it's out of phase will be dependent on the length of travel back and forth here. And then we can measure the interference patterns to be able to see how much out of phase it was. And so this is how they measure the gravitational waves with LIGO. And it's also how they got the photo for the black hole. The Event Horizon Telescope is multiple different radio telescopes all across the world, and they overlaid these interference patterns just over and over until the final image came out. And so we use this technique in radio, And we're able to do that because, as I'm sure a lot of you might know, is that one of the challenges with telescopes is the angular resolution. So here we have some evolution of, as the telescopes got better, we were able to image things better as the angular resolution increased. But by using interferometry, we can go even further. So one way that we can increase the imaging capabilities of telescopes from this angular resolution challenge is to just make like a bigger telescope, a bigger diameter, but there's only so big you can make a telescope. That's the whole reason why the Event Horizon telescope had to make an array all across the world, because the only way that they were going to be able to image the black hole was if they had a telescope with a diameter was the whole size of the Earth. And so instead, they had multiple different telescopes in an array to get these interference patterns to get a really good image of the black hole. But there are some limitations here. So the distance between the telescopes, it's called the baseline array, or it's called the distance. And in radio, the angular resolution can be about 20 micro arc seconds. So we can get a pretty good resolution in radio, but in optical, and this is from the Chara array. So if you come to the talk tomorrow, I'm sure Hal will be able to talk more about Chara, right? Because I think he was the one that started it and built it and whatnot. And so in the optical wavelength, the baseline limit is we can only put telescopes about 100 meters apart before we start to lose more than we gain. So this is the big limitation, because when light comes in to the different telescopes, we want to be able to interfere with it to reconstruct an optical image. But a big challenge is also transporting those photons. So we can think about light as little packets of energy called photons. And we can transport light using fiber optic cables, but they are really lossy. Sometimes when we are transmitting photons through these cables, there's like a 60% chance that you could just lose the photon if you are transmitting it with the quantum light, essentially. But so this baseline distance is a really big challenge that we can tackle with quantum. So as a brief overview, light, we know, is a wave and a particle at the same time, but it also has quantum properties. So one of those is superposition. If you have two packets of light, they can be either in a 1 or 0 state, let's say, and then the other one can also be in a superposition of 1 or 0. So we have these two photons that are what we call entangled. And so anything that happens to this one is going to happen to this one. But as soon as we measure it, it will take a definite state, and the other one will take a different definite state that's dependent on the first one. So we use this at the Quantum Center as a big resource. We say that entanglement is a resource, and we can also use that in astronomy as well. But this is another limitation that we have, is the Heisenberg uncertainty principle. So if I have a wavelength of light, we say x is, let's say we can only know the position of a wave or how fast it's moving by giving and taking one or the other. So if I want to know where the wave is, I'm not going to know how fast it's moving. But if I want to know how fast it's moving, I'm going to have to lose information on specifically where it is. And that is the limitation here. So one of the first solutions that was proposed by a guy named Daniel Gautzman in 2012, he came up with this idea that we could use these quantum properties in optical telescope arrays. So this is a schematic that he came up with, and we have two different optical receiver telescopes, and between them we have a from here we're going to emit the entangled photons. So from a lab here, we emit one entangled photon to here, and then another entangled photon to here. And so if the light is coming in from the star, since in the optical range, another thing that's kind of a difficulty with it, with getting a lot of photons from space is the number of photons. So since we can say that, let's say one comes into here and it interacts with the entangled photon that we sent here. And so anything that happens to this one is going to happen to this one over here. So if I have these two entangled photons and I'm getting more and more photons from whatever object I'm trying to observe, then we can essentially have an arbitrarily long baseline between these two observatories, because whatever is happening to here, this entangled photon, I can recreate that information over here and then create an interference pattern to reconstruct the image, like we saw earlier with the black hole image. And the way that we transport this information from here to here is by using a technique called quantum teleportation. And this is a simple schematic of that here. So we have Alice and Bob, and just like if there's an entangled photon sent to two observatories, we send two entangled photons to each Alice and Bob. And Alice wants to send this piece of information to Bob here. So she's going to have she's going to take this information and encode it into the entangled photon that Bob has a pair of. And then we will use classical communication. So Alice is going to call Bob and say, hey, measure this photon in this specific way. And so he's going to measure his pair that he has and be able to reconstruct the information that Alice has. And so the information from Alice has teleported over to Bob. And we can do that with the light that comes from stars that we observe, and to transport it to a different observatory off. And I just wanted to give a few examples of quantum applications that are already in play. So at LIGO, they use what we call quantum squeezing, and this is an actual setup of how they squeeze the light that comes in. And so since we know light is this wave here, we can squeeze the phase of the light to be able to get more information about the amplitude of it, or we can squeeze the phase of it to be able to get more information, other way around, squeeze the amplitude to be able to get more of the phase information of the light. And so from doing that, we've been able to really up the detection of gravitational waves that we can get from LIGO. So this is from 2015, and the purple is a lot of noise. And then we have the green here, which is a signal that we're trying to get. And after using these quantum techniques, we can really reduce the noise and be able to see the signal much better. And so before we had like less than one detection per month, but now we have about one per week after using these quantum techniques implemented in the observatory. And so to be able to take those types of techniques and put them in the optical range can really, we can achieve a lot more in optical astronomy. So one of the things is we'd be able to study the dynamic of the galactic center and the black hole's event horizon by using these techniques in the optical wavelength. We'd also have improved imaging of exoplanets and allow new stellar types to be imaged, including compact binaries, which is the types of things that can create gravitational waves. Okay, and as well as a couple other things down here at the bottom, because the biggest thing about these quantum techniques is we're really just sort of increasing the sensitivity of our instruments, and if we can do that, then we'll just be able to see more and observe more and whatnot. And yeah, and that's all. Thank you.
She's got a question.
What is the event horizon?
Yeah, that's a good question. So at a black hole, the event horizon is where...
Oh, right. The part of the space of no return.
Yes,
I was thinking
right.
of the center.
Yeah.
Sorry.
Yeah, it's okay. Yeah,
The event horizon is like and then
Yep.
it's the black hole.
That's an interesting
Yes.
way to describe it.
That's exactly, yeah.
Hey,
It's
I
as
can
technical as I
describe
could get. That was
Yeah.
fantastic.
Yes.
How many photons would you need to really generate a picture that's going to be useful?
Yeah, that's a good question, and that's why. So, do you mean like from space or from what we're putting
Well,
from the
then
lab?
I guess you got to have the quantum to transfer the information. So
Mhm.
I'm assuming that you have to generate a lot of these entangled photons to get the information from AB.
Yes, yeah. So we would have to essentially generate as many entangled pairs as how many like pieces of light information that we want from here, and that's why a lot of people are talking about we should really put something called quantum memories or almost like quantum hard drives at each of these places, because if we don't have a hard drive, then we'd essentially have to send a photon right when one from a star comes down to interact with each other, and that's just not very feasible. So if we had a hard drive here, then we really wouldn't have to send all that many from our end, and then we could just let it sit and collect as many photons as it can from the object. Does that answer your question?
Yeah, I guess that's one follow-up question is how accurate do you have to be in tracking the object in the sky to really keep that going? I mean, is the atmosphere like a problem since it's been a problem in the past?
I would assume so. I would assume that the atmosphere would play a problem just as much as other like ground-based optical telescopes. And so I think the idea would be if we had that hard drive there, then we could have it pointed at the object and almost take a pause when we can't see it anymore, and then open it back up to be able to keep collecting that same data. Yes.
So it sounds like since you have to generate the entangled pairs as you're observing, it sounds like this is a single observation, not like multiple nights, multiple weeks, multiple months, which would create an effective aperture the size of the orbit of the Earth if you could carry it out across months.
Yeah. So the scheme that this guy proposed, you would have to send them at the same time. But there was recently, like a few weeks ago, there was a group from Harvard that put out a paper in Nature where they demonstrated a proof of concept of this, and they implemented the almost like a really simple version of the hard drive, quantum hard drive, in each of the locations.
Okay,
And
that was my
whatnot.
next question, whether that would allow multiple day and week and month observations.
Yeah.
On hard drive.
Yes, it would. Yeah.
So
Yes.
the other one, you said you had only so much distance between the two. So how much is B the distance between them?
100 meters?
That's so that's what is the advantage here is this V distance can be as long as you want it to be.
Oh,
So you're not
'Cause
limited.
the other one was limited, right?
Right, because it had to be physically connected. But this one, they can be at any distance because they don't have to be physically connected to each other to like transfer the photons information that comes from the object. The only reason they would have to be connected is for this. So the real limitation in this scheme for B would be how far can we send entangled photons, and that problem is much easier to tackle than the regular optical baseline transporting photons between the two. Does that answer your question?
Yeah. I had one other question, but, oh, I know what it is. So I know the James Webb was put up for radio astronomy, right? So does it have something on there with the LIGO to make it clear? That's what makes a clearer picture? Or?
No, it doesn't have any. If you're asking if it has like the quantum type techniques, I don't think so.
So would that be something in the future if they?
For James Webb,
No, but for another telescope.
I'm not sure how it would work if you wanted to do something.
In space.
Yeah, like that's sent into orbit. The only things that have been proposed so far have just been ground-based things.
Just as curious.
Yeah, it's a good question though.
I think these quantum applications post-state
Lani,
when
what do
they
you
lock down.
what do you think
design
this
of James
line
Webb
of research will?
Right, I'm sure. Right.
What will we
Right,
learn
right.
from it?
15
Do
years.
y'all hope to find out?
Whatever.
I mean, what
I understand that. But I meant
what's the
for-
possibilities here?
Yeah, with it specifically in the astronomy applications, it's just a more
Just curious.
sensitive measurements of in the optical range,
Mhm.
But beyond that, we're also there's other applications that specific like type of interferometry that we do in our lab that would apply to this. It also applies to biomedical imaging. So my advisor worked on a project where using this same technique, he was able to image breast cancer cells better than what's currently implemented in hospitals and whatnot. And so that's another big application in this field that we like to kind of contribute to as well. Communications, secure communication networks that's completely tolerant of or intolerant of eavesdroppers.
Well, there's
Whatnot.
a good thing to go after.
Yeah.
You go ahead.
Well, yeah, how far can you send a quantum, entangled quantum photon?
Yeah, that's it. So that is a big current research project that a lot of people are trying to really extend the distance of how far you can send one. Right now, it's about the kilometer range is the best to where when we send the two entangled photons, they're still entangled by the time they get there, and we don't lose one in the fiber. Yes.
It might tie into that a little bit too, because I missed your UTC talk
Mhm.
because I was probably in the planetarium or something. But thinking about, you got the Event Horizon, which is only just a handful of places that would actually work to build that. When you have this, or the thoughts of, it depends on that spacing. Like, you almost like you have optical telescopes all around the world working together. Like, I guess the resolution scale would be immense
Yeah.
if this actually was able to tie in, let's say, hundreds instead of just 5.
Yeah.
You know,
Yeah. And I think that is one of the sort of like super long term kind of ideas. Another way, we can actually send entangled photons from satellite as well, I believe, and so that's sort of another avenue that people would be able to look into, is rather than having a lab going to the 2 telescopes, maybe having a satellite sending the entangled part, and then you wouldn't have to worry as much about losing it in the fiber, maybe.
Yeah.
Yes.
You were talking about LIGO. I didn't catch your seminar either. But when they detect those gravitational waves once a week, what are those waves? What are they indicating is happening out there? Could you shed a little light on that?
Yeah. So it depends on the information that they get from the wave. So we say that gravitational waves can hold memory, or that they have memory, and so we can analyze the wave that comes in, and we can figure out whether it came from 2 black hole collisions or from a black hole and a neutron star colliding, and there's even some theoretical predictions that if we can make LIGO sensitive enough, we should be able to detect the gravitational waves from the Big Bang, because those are still out there.
You're serious.
She's serious as a heart attack.
I thought you would say that.
Do you have to send these photons in a fiber optic, or can you just transmit it through free space with like laser? I mean, it's a laser anyway, right? Or something.
Yes, I think currently the sort of, I guess, best implemented is through fiber, to be able to implement all of the sort of techniques that we want to be able to use. But we can still do it with satellite as well, but it's a little bit, I think it's a little bit harder. I'm not exactly sure the comparison of those 2.
So, how long will it be before we can address you as Dr. Lani?
Oh, maybe about 5 years. Yeah. Yeah.
Quicker than that, I would imagine.
Would you work in Oak Ridge, or where are you going to go?
I don't know, wherever I can go, I guess. I'm sure they'll send me to Oak Ridge at some point, just because a lot of the faculty collaborate there.
But take him wherever adventure takes you.
Yeah, exactly.
boy, that's smart advice.
Mhm.
Hey,
Oh, yeah.
just something I thought I'd say.
No. Pretty good. She didn't get that from you, right?
No, she didn't get that.
They got that from me.
Her mama's pretty sharp. This is fabulous.
Yeah, that was awesome. Thank you very much.
Glad I showed up.
Yeah.